Without much ado, I kindly ask Professor Döllner to start his keynote presentation. Thank you.
Yeah, thank you, Thomas Blaschke, for your kind introduction. I'm Jürgen Döllner. I'm with the Hasso-Plattner-Institut at the University of Potsdam. I hope you can hear me and everything works fine. You should see my shared screen. I hope that's fine and this is working. Yeah, first, let me introduce myself with a few words. I'm working in computer science. I'm a computer science professor at Hasso-Plattner-Institut, and our goal is to construct, to analyze, to design systems, software systems that are based on or use visual computing, geometric processing as core elements. So this is this is my research. My research is focused on that kind of system engineering. For a long time, we work with geodata, with georeferenced data. And recently, in the last couple of years, we started to ask ourselves, what about artificial intelligence with respect to GIS? And this is what I would like to discuss in my talk. I would like to discuss a little bit the wording, artificial intelligence, which would lead to a long discussion, but we will not have this long discussion here. And I would also like to show you some examples of what you can do combining artificial intelligence methods and techniques with geodata. So this is what I'm going to talk about in today's speech. Let's start with a very short and general overview of AI. So what about artificial intelligence? It's one of the greatest buzzwords used today in press, in almost every publication you can find. This is a phrase that is used. Even politicians tend to use this phrase. So let's ask ourselves, what is artificial intelligence? Well, it's basically coined and shaped by science fiction. This is where this word came from and is still defined to a certain degree by our perception of scientific stuff. For example, HAL 9000 was one of the first intelligent computers that appeared in the movies. And Space Odyssey, for example, was one of the greatest incarnations of artificial intelligence. Well, this is at least the point of view of these peoples in entertainment. But scientifically speaking, it's not directly this way. We have to be much more precise when we talk about artificial intelligence. There's a fundamental problem behind, and it's still not solved. And it's really a fundamental problem. The problem is, what is intelligence? Is there a kind of human-specific intelligence? What about the kind of natural intelligence? And what or when starts intelligence to be artificial? Also, we in computer science, we ask, is there a kind of general purpose intelligence? Maybe this would be core part of artificial intelligence. Whatever you would like to investigate here, at the end, you also have to ask, is there a dark side of intelligence? Because intelligence, as we all know from our daily life, has many fold facets. And so at least here we see it's not easy to talk about artificial intelligence not knowing what intelligence really means. There's a number of controversial assessments you can read, and recently these assessments tend to start very, very objective in a sense that say, analyze clearly what AI can do and what AI cannot do. For example, it's almost clear that human intelligence will not be replaced by artificial intelligence. There are many misconceptions around AI. There is also a more technical view. It's a glorified signal processing tool. Hope that this will help to see better the slides. I guess it should now be maximized. AI, once it's used in society, in economy, it typically does not look like AI. For example, the autopilot mode of a modern airplane. This is not considered to be artificial intelligence, but it was considered to be artificial intelligence at the time it was introduced. So it's more or less a moving front, yeah, what we as society, what we as scientists consider AI, but there's not a very fixed definition. There's not a sharp definition. Well, let's go on and see what this could mean for our scope. First of all, I would focus on technical aspects. So artificial intelligence is at the moment mostly associated and mentioned and cited with respect to machine learning as key ingredient, as key element of artificial intelligent solutions. And of course, within machine learning, deep learning plays a major role as it is accelerated by modern hardware. So recently, in the last 10 years, let's say, all this exploded almost. Exploded in the sense that hardware came available, that big data became available, and many other key factors that impact artificial intelligence moved to such a point that it allows us nowadays to build, to use, to operate applications and systems using artificial intelligence. Of course, this is this illustration you see it's quite limited. It reduces somehow artificial intelligence to a special application case of machine learning. But in reality, in the reality of IT systems construction, there are much more factors, much more topics, much more technologies that contribute to artificial intelligence. For example, analytics in general, also portfolio of analytics methods. AI accelerators are a prerequisite for operating such applications. Computer visions in many application domains plays a major role. Text and speech recognition, as well as knowledge representation and reasoning are other key elements that contribute to modern AI-based IT solutions. But when you look at it, there's nothing special for geodata. There's nothing specific for geoinformation. These are the general technologies that can be used, that are used for AI-based IT. So at the end, AI is now changing the way IT solutions are designed, built, and finally operated day by day. And AI is not limited to a specific application domain or a specific application area. It's finding its way in all industries. Having that said, the question is, how does AI find its way into geoscience? Well, let's start with, I will illustrate this point for 3D point clouds. 3D point clouds represent my major field of interest at the moment. So I decided to use this field of this topic, 3D point clouds, to illustrate a little bit how AI impacts the way we construct geodata applications, geodata systems. First of all, let's start with what are 3D point clouds. Point clouds represent unstructured sets of three-dimensional points, possibly attributed by some additional data, for example, RGB color information. But if captured at a certain density, we can do right away wonderful things. For example, really, truly immersive visualization of indoor environments. For example, this is a dense point cloud taken from a castle, and with a VR headset, you can dive through this point cloud, and without having to do any modeling, you just get a kind of spatial digital twin for this specific example or in such a specific indoor environment. So point clouds are very powerful for creating and visualizing spatial digital twins. They also serve to a certain degree as representations of reality, as is representation. For example, here, construction work, and the point cloud captures everything, including materials stored here on the site and the current status of this ongoing construction work. But the key point is we do not have to model anything here. We just use the point clouds. On the other side, point clouds, once they get dense, they are perceived as 3D models. For example, this point cloud-based virtual 3D city model of Landshut, which was recorded and reprocessed this data set at Hasso-Plattner-Institut. These are some obvious applications, but the question is, where can AI contribute here? Let's have a look on the specifics of 3D point clouds. Point clouds, first of all, are generated by a diversity of hardware devices. We can use remote sensing, photogrammetry. We can even synthesize 3D point clouds based or taken from 3D models, deriving these point clouds from existing 3D geometry. And of course, we can use procedural generation techniques to synthesize 3D point clouds. So most of you are very familiar with these techniques, and most of you will have had contact already to many point cloud applications. Recently, there was a key step, as in my point of view. A few months ago, a few weeks ago, Apple introduced a new generation of iPads having a LiDAR sensor at the back. Yeah, which means that now the capability of capturing the environment based on a discretized approach, taking irregularly sampled point clouds, is now becoming a feature of common hardware. Even the next generation of smartphones will step by step include sensors like the iPad already provides. So we will have a wonderful future with respect to 3D point clouds. We will be able to capture them at almost no costs. For some application domains, this will be sufficient. Other application domains, of course, will require more precise, more professional technology, such as LiDAR scanners. So, but in general, the key movement or the key direction is that point clouds appear to become a fundamental data source that allows us to capture spatial reality. So the question is we are fine with this? Is this yet the answer to modern GIS? The answer, unfortunately, is no, because point clouds tend to be very large and tend to be discrete, unstructured, having almost no structural information. Although they can approximate any shape, any topology you find in a spatial setting, or any geometry, this is sometimes insufficient for building an analytics applications, simulation applications, and any other higher level application or domain specific functionality. So point clouds are stupid in a sense, put it in simple words. And on the other side, they are very handy. They have this wonderful probability and characteristics to be absolutely general purpose data representation. They make no assumptions about the density of the points, of the sampling patterns, or of their statistic properties. So it's a simple and powerful approach to geometric modeling. However, point clouds by itself do not have any semantics information. And this is a key point to be addressed by artificial intelligence. If we go one step further and think of capturing point clouds in regular intervals or even in real time, we come up with a concept called 4D point cloud. It's a spatio-temporal point cloud. For example, taken by a group of vehicles that cruise through the city every day, every hour. You could imagine having a constant stream of point clouds being delivered to some centralized place and reflecting the spatial reality at certain points in time. Of course, the key problem here will be to eliminate redundancies. They are extraordinarily redundant in the sense that they consume a lot of memory, and of course, redundancy should be eliminated. Also, they have to be regularized. They have to make more adapted to some standardization. They have to be mapped on the 4D point cloud. That is, as every point cloud is very, is taken at a certain point in time and under certain conditions, for example, weather conditions or driving conditions, it's a key step to unify these representations. And here again, the question is, can AI help? In that sense, I would like to think of having an AI-based interpretation of point clouds. So interpretation is a very general term. If we interpret point clouds, we basically derive some higher level information. We take out and distill higher level information. For example, semantics, of course, typically as a pre-processing step, we compute segmentations and classifications. We can build spatial models. We can derive descriptions, higher level descriptions. And all in all, we can represent phenomena. We can get out information about phenomena. For example, are there people riding a bike? Are there cars moving along streets? So this is what we call phenomena, spatial phenomena. There's a growing interest in AI related to 3D point clouds. Just to give you one example here, it's a GitHub site, awesome point cloud analysis. It's a collection, I really appreciate this collection of all papers from the last 3 to 4 years related to artificial intelligence and point clouds. This site contains more than 400 papers right now, and it's growing and growing. So this somehow indicates that we started and we are doing more research on this interesting fundamental data set called point clouds related to machine learning and deep learning in particular. So what can we do? This is part of my work as well. In my group, several scientists and myself, we ask ourselves, what is specific for AI related to geoinformation? Of course, AI tends, and machine learning in particular, tends to be powerful if you talk about fuzzy phenomena, if you talk about fuzzy data, and if you talk about objects that in general can be described by example. If you think of vegetation, this represents a very suitable category for machine learning because we can describe vegetation by example. That is, we will get a lot of valid training data, ground truth data even. And what is a tree? This is a very difficult question, and thinking in procedural programming, you will not come to an answer. You will never come up with an algorithm that defines a tree in terms of procedural programming. However, if we apply machine learning and deep learning, this can be answered to a certain degree, coming close to 95% even in our test data, because we train the system for the trees we are interested in. For example, here we have a module in our platform that detects vegetation. We can also detect changes. Here's the key question for AI, for machine learning, is to eliminate those points that are irrelevant for detection, for change detection. The elimination of not relevant, of irrelevant, of noise points in point clouds is essential, and it can be solved by machine learning because cleaning here is again based on training as well as on some more fundamental pre-processing techniques. But if we do so, we can clean up a point cloud and concentrate on the point subsets that should be compared. For example, here we see some new buildings have been erected in a city. We can also apply machine learning for mobile mapping scans. Key question here is what objects have been captured. So we ask for object detection, for example, cars, vegetation again, facades, city furniture. A more specific example represents infrastructure, because here the definitions are sharper. So we can better train the system to detect railway elements. This is an ongoing project with some companies that take care of maintenance of railway systems. Especially they focus on the surrounding of a railway path, because they would like to detect changes, and in a sense they would like to do maintenance and predictive maintenance. So this is a core task in managing and maintaining such technical infrastructures. We also work with data sets that have many data layers. For example, the ground penetration radar delivers us a complex data sets, not only 3D points. And this based on this ground radar, we reconstruct by means of point clouds the structures hidden below surface. Also, we focus at the moment on removing artifacts from mobile scanning, because most point clouds are characterized by many artifacts, many disturbing artifacts that make it difficult to process these point clouds unless they are cleaned up. So this is what we also investigate. How can we eliminate, for example, shadows that result from the mobile scanning process? How can we eliminate what we are not interested in? For example, people walking along streets. Once again, this is based on machine learning, because machine learning allows us to train the system specifically. In particular, for this example, here's the city furniture, also traffic signs have been extracted. This is a kind of base demand in industry to have a good review, a good list of all objects that can be seen and found in the street space in general. And we use a double-fold strategy. On the one hand, we apply on 3D point clouds an image-based classification. So point clouds get used as a source for rendering artificial photographies, and later we analyze objects in these artificial synthetic photography. And on the other hand, we apply deep learning directly on 3D point clouds. These are at the moment two main approaches. How can machine learning be applied on point clouds? On the one hand, based on image vision approaches, whereby the images are synthetically produced from point clouds. Of course, if you have one point cloud, you can generate within 1 second several thousands of images. So this is a key advantage, that you can approximate the scenery by taking many photos at no cost, because this is done during a rendering process. And on the other hand, operating directly in the 3D point cloud space gives you other opportunities. So at the moment, we believe that a hybrid combination of both approaches works best for industrial solutions. We can even come up with component classifications. For example, if we detect persons and if we detect bicycles, and if they share the same space, we can conclude that this is a person riding a bicycle. So now, at this point, I would come to some conclusions. You have seen machine learning and deep learning works very well for point clouds, because they allow us to distill semantics, and to distill semantics in a very focused way. But what will be the result in the long run? What can we expect? There's a nice theoretical finding, and this is somehow the explanation for the power of machine learning for point clouds. 3D point clouds can be considered to be a form of natural communication. Point cloud corpora, if you take all point cloud sets together, you build a corpora, have similar statistical properties to natural language corpora. This is an amazing finding, that statistically speaking, both corpora are very similar to each other. And if so, of course, we can apply techniques and applied for natural language corpora to 3D point cloud corpora. We can exploit these technologies for geodata, for 3D point clouds. In that context, we speak of spatial utterances, because typically utterances are based on language, but in this context, in our context, point clouds represent simply spatial utterances. And this leads to a theoretical finding, which is called the Naturalness Hypothesis for point clouds. Almost all 3D point clouds of spatial environments contain content that is statistically repetitive and highly predictable. That is because in most applications, in most domains, we will find more or less same objects, whose characteristics can be trained, are known to a certain degree in knowledge databases. This is why machine learning works very well for 3D point clouds, although 3D point clouds seen from a classical procedural programming approach are awful because they do not have any structures, they do not have semantics, they are stupid collections of points. However, combined with machine learning, we somehow introduce inject semantics into these spatial representations. Taking into account that the generation of 3D point clouds becomes a common technology, becomes a common feature of many, many devices, we can think of the combined application of machine learning and point clouds leads to technology that allows us to build almost in real time spatial digital twins. And we can do this because they have this naturalness property. Going one step further, we also see that AI will definitely simplify geodata processing pipelines and geospatial modeling. As there is a vanishing need for explicitly modeled data, as there's a vanishing need for multi-layered 2D and 3D spatial models. Typically, and this is shown in the upper part, we use raw geodata to derive models and combine these models, blend these models into higher level models, and this is what is what serves as input to applications and systems. If you think of 3D point clouds, we basically can skip these inner parts. We directly operate on raw point cloud data, and in the middle, the processing itself consists in a machine learning based interpretation, and at no point in time we derive explicit models, because most things applications are interested in systems can somehow be covered by a real-time interpretation of point clouds. That means in the long run, we can avoid this explicit modeling part, which forms the major part of GIS technology. So the more we distill models, the less details become and the more assumptions we include. So abstraction grows, but the detail degree falls down. And this is what we avoid if we always operate on raw point cloud data and we do not derive models. Instead, we interpret once again the original 3D point cloud data. For example, we can take measurements. This is the most simple example I found. Why should I reconstruct a roof model if I'm only interested in the outside measurements? Of course, if I construct a roof, I have to build a CAD-like model because it's needed by all other processes. But if I just want to look at roofs and to do some calculations and think of having a clean point cloud that shows you and operates only on roof points, then it becomes obvious that we can skip the modeling part. Also, we can conclude that in the long run, and this is my point of view as a software engineer, as a computer science expert in that field, what I can observe, it's based on my observation at the moment and in the recent years, the AI-based approaches at the end lead to a reduction of IT software complexity. In simple words, the programs, the software becomes simpler. Becomes simpler because many parts are put into the black box of machine learning. Of course, you have to provide and you have to configure well the training parts. However, once you opt for this approach, you can eliminate many procedurally programmed parts that tend to be heuristically based and have grown over decades and contain more exceptions than regular cases. We all are familiar with these enormous source codes that try to handle exceptions and try to handle the regular cases. And all this basically can be converted and somehow sublimated in AI-based solutions. So this is these are the main conclusions. Once again, based on the natural hypothesis for point clouds, we will see that the geodata processing pipelines and geodata modeling and the geoinformation systems in general will change. They will change their implementations. They will do less modeling, they will do more interpretation, and as a side effect, as a very positive side effect, possibly the software complexity will also be reduced. So that's a key message I would like to discuss with you. Yeah, and if you would like to contact me, you can reach me at Hasso-Plattner-Institut. You can also reach the principal scientist in my group, Rico Richter, who is responsible for the operating point cloud platforms in my department. So thank you very much for your attention. I hope the transmission was fine and you could see the slides after having solved this first obstacle in the beginning. Yeah, thank you very much for your attention.
Thank you very much, Professor Döllner. There are a few minutes left for questions. I noted down a few. You have a chance to write them. There's also questions in the chat. There's already one in the chat which I would also come up with. It's all about training data. As we know, AI in general, but when you particularly, if I may add to the question in the chat, when you mentioned that you would like, obviously, you like to remove objects like people walking on the street, you like to remove that. And it's probably hard to train what you don't want to have, and it's harder to train what you don't want to have in your data rather than to train what you're interested in, right? Is that correct, or how would you do that to? In machine learning to remove objects like people walking on the street?
Yeah, that's not, this does not have a simple solution. Actually, we apply a hybrid strategy. That is, we try to eliminate as many points as we can. We use standard processing techniques without machine learning even, yeah. It's just a question of reducing the number of points. And it all depends on the application you have in mind, yeah. So we, at no point we define a certain classification of object categories, because every application in general has more or less its own way of thinking about relevant and irrelevant objects. So to eliminate the data, we apply manifold strategies, yeah, in the hope that at the end we have eliminated most of the irrelevant points. Yeah, but there's not a clever way to do it. There's not a single way of cleaning the point clouds. And the training data, of course, is in general in machine learning is a key part, because if it all depends on the quality of your training data. However, in geoscience, we have almost ideal, a perfect situation. We have valid data sets. We have an incredible amount of data that can become the rule, or has the rule of ground truth data. Just for 1 second, compared to social media, here you don't have this long history, yeah, of decades of building clean and checked and controlled data sets. And this is also a bit the explanation why machine learning for geodata works well, because the data that is available can be considered a very valuable data source. This is just because this is a domain where data quality was always a big issue.
Okay, thank you.
Just one remark, maybe it's interesting for students if they want to think about master thesis topics. For example, a very convenient and effective way of producing training data is to synthesize artificial virtual cities, placing different objects and simulating, for example, a mobile scan, yeah? So you can better find out how certain objects impact your cleaning algorithm, yeah? And this is the way also you can produce good training data. It's synthetic training data, but it works perfectly well.
Okay, thank you. Now, there are now more questions popping up, but we have basically reached the end of this session. I think I would like to conclude here, maybe with one personal comment, because we have not so much from a computer vision point of view, but when trying to deal with point clouds, we try to use segmentation for a while, and it works, but it would never work in real time, at least not the approach we've taken. But I really see the progress which has been achieved over the last years. And in one of your last slides, you said I think you verbally said you can avoid explicit modeling of objects. And this is the key. Even though I personally always liked to do explicit modeling of objects. But if you want to be fast, if you want to be almost near real time, this is probably the solution to go through the instant point as a subpoint cloud rather than to explicitly model that. But do you want to have just a very quick comment on that? We not have much time left.
I think the key difference is, on the one hand, you don't do general purpose modeling. It's always a modeling that focuses on the needs of the specific application as it is performed in real time, possibly in real time or in near real time. Yeah. And the second point is that using this idea of interpreting point clouds, not compiling point clouds into models, instead interpreting point clouds at runtime. Yeah. If you think of doing this interpretation at least in 1 millisecond, you end up in explicit models. This is what you give to the applications. The key difference is they are not general purpose, they are not pre-manufactured, and they are instantaneously generated. But of course, applications want to have object descriptions. They don't want to have, for example, an application would like to know where's the traffic sign. And the application does not want to have a subset of the points that represents a traffic sign. So there's explicit modeling still there, but it's not any more general purpose and it's more instantaneously generated.
Okay, thank you. Thank you, Professor Döllner.